The following video exhibits a prototype used to determine the dimensions needed to fit the real-world specifications for an oil remediation device for oil spills and things like that, and even possibly other waste materials that need to be burned that can't simply be dumped. So what we are looking at here is a propane assist ignition process. We are using propane to initiate the combustion, which will then be drawn back and turned off completely once the interior combustion chamber heats up. And then the oil spill sludge would be pumped into the device, and there's a lot more than meets the eye that we're looking at here. There is actually a chamber within inside a chamber. We have a outer shroud that is preheating the combustion air before it enters the cyclone. Right here is a closer look at the effects of our secondary air. You can see those blue rings of fire there. The primary air is not turned up enough for this amount of propane, but I just wanted you to be able to see the effects of that secondary air swirler. We probably would be well suited to put a longer nozzle on the front of this. That's with the secondary air turned off. And we are going to go ahead and start the oil at this point. You can see the oil slowly traveling up the line there. We start off with a small amount of oil. The propane flame is still going on inside the unit. We're just not wanting to waste a bunch of it. And we wanted to practice doing this with a small amount of propane ignition. And that little bit of smoke that you see is from some oil that dripped off the valve onto the outer casing of this device. Because as I said, there's an air preheat shroud going over the actual combustor. There you can see now we're starting to burn, and this is right around 58 liters per hour we're looking at here, a fairly high amount. It draws back a little bit, and I'm just kind of learning how to use the device at this point. Now we're at way over 60 liters per hour. I draw it back down to about 50 liters per hour in this first test, because I wanted to check it out. That's with the secondary air on, and in a second here I'll turn it off, and that's with the secondary air off. And the benefits of the secondary air is going to make it wind resistant. When this thing's on a boat and we've got, gale force winds going on, we're going to want to be able to run this thing. So a shield around the top end of this would enable us to run just fine in extremely high winds. And there is also a large portion of the combustion is taking place inside of this chamber. We are looking at a chamber that's 9.5 inches wide, and I believe the interior chamber is 8.5 inches. So we have a 1/2 inch preheat zone that the air travels over before it goes into the combustion chamber. And as you can see here, I'm just messing with the secondary air. By this point, I had to put a shroud because we keep melting the tube. The secondary air test, as you can see here, it does have a dramatic effect when it's on versus off. Right now it's turned on. We get a little bit of the Condona effect, or the Coonda effect going on right there, where it's drawing the flame back over the combustor. But I just wanted to show you guys that, how it can tighten the flame up. I don't think we would get that Condona effect so much with the extra shroud on the nozzle there. And here we really crank this thing up to some high power. I think this is the scene anyway. I'm just kind of walking along with you here. It takes a minute to get going good and heat it up right. But once you're going, it can produce quite the fireball. At some points here we were hitting over 2 liters per minute, and for the most part in the testing that I saw, the most stable combustion for this particular size is right around 50 liters per hour. So we're at just under a liter per minute on combustion, using 0.4 cubic foot of space, about 750 cubic inches. And I'm just kind of testing the secondary air at this point. You can see some smoke kind of coming off of it there. A lot of that smoke is actually ash. There's a white ash that comes off of really dirty waste oil. In this particular case, we're using some very thick, dirty bus oil that come out of some school buses. And I don't know how close of a simulate this would be to our crude oil that's being scavenged off the seabed, or off the sea surface, I guess I should say. Not the seabed, obviously. I do believe this would be able to handle some water also. Right now I'm just kind of trying to dial in the fuel and the air ratio properly. It can put off some pretty big flames, and one of the ways that I use to calculate the actual size of the device that we would want to use is we come up with an optimal operating range on this specific design was at 50 liters per hour. So, and that was at 0.43 cubic foot. So if we take into consideration the 4,260 liters per hour that are specified by the requirements of the skimmer pump, we come up with, if we divide that by 50 liters per hour, it comes out to 85.2. So if we multiply 85.2 times 0.43 cubic foot, that comes out to 36.63 cubic feet of combustion zone that would be required to burn 4,260 liters per hour, or the, I can't remember what it was, at 19 gallons per minute. I had 640 barrels a day, I think you said. I didn't do my math on the gallons per hour. So if we go 19 times 60, 19 times 60, okay, so that's 1,140 gallons per hour. I have that wrote down somewhere. I'm just not seeing it in my book here. But I believe something approximately 5 foot tall by about 3 foot wide on the combustion zone diameter. The total width would be about 3.5 feet, because we're going to want that air preheat shroud going over the actual combustion chamber, because if we were looking at the actual combustion chamber skin, it would be glowing red hot, and we don't want to waste all that heat, and we don't want to be burning up the auxiliary equipment from the infrared energy coming off of this thing, and we don't want seawater and sea spray splashing up on metal that's that hot. It could cause corrosion issues, and all kinds of other stuff could happen. Maybe some stress cracking and things like that. But I just wanted to turn this thing up way past optimal. This right here is pretty high output. I believe this was about 1.5 to 2 liters per minute. So double what I determined to be the optimal conditions. And the only reason I'm saying that is when we're running this much fuel, our interior cools off quite a bit. A lot of heat goes to vaporizing the oil, because there is no oil atomization system on this setup. We're simply using the heat from the combustion to vaporize some oil that's puddling into a tube that is facing at a tangent to the rotation of the air there, and it's being preheated by the hot preheat air that's wrapping around the combustion chamber itself. So that's kind of how this thing is set up. Now, I have done this in some systems before that don't have that outer preheat shroud, and it does perform fairly well. You can get a really nice burner, but I believe it to be suboptimal in that configuration. So by throwing a little bit more money at it, we can get a device that can easily vaporize any water or sludgy material far better than if we were just to have just a combustion chamber in itself. If it does become cost prohibitive to design it the way we're looking at now, we can remove the air preheat shroud that's going over the combustion chamber. As I said, it's an 8.5 inch combustion chamber, but we're looking at a 9.5 inch diameter shroud there. So we have a ½ inch on each side where that air passes over. And you can see here we are running at enormous combustion rates. This may be up to 4 liters per minute, but the buildup inside of the combustion chamber could become a problem after some time, and we would have to stop and clean it out running at this rate. I don't know how well it's vaporizing everything inside of there, and that is one of the reasons why I rated it at a lower rate than what we're looking at right here. But in practice, this could be done. However, I don't know how well something like this would do out on the ocean, out in the wind, with a flame this big sticking out of the top of the device. It is a fairly lazy flame, but it could work, and we may decide we don't want it to run in a vertical position. We may be able to run it horizontal like we're looking at here, And the reason why that would be better is that a guy could clean it out a lot easier with it laying on its side than if it was sticking up. And also, I don't know how the oil pooling up in the bottom pan would affect performance with it in the vertical position. We can do a test with this device in the vertical position if we want to. It's just not currently set up for that right now. And I did that because we are facing upwind here. That way it's not, it doesn't have air blowing in its face affecting the flame. I wanted you guys to look at the flame without it being just blasted all the heck with the wind. I wanted you to see the flame in its true form the best as possible during this test. If we were to have it facing straight up right now, it would be blowing towards the right if we were standing in front of it, you know, in relation to this camera here. And I didn't want to do that. So this right here is a fairly optimal setting. I believe by now our secondary air hose has melted from the Combustion effect. I can't pronounce that word. I think I'm saying it wrong. It's either Combustion or Combustion effect, which is where the air is drawn back on the combustor itself. But an extension on the nozzle there would prohibit that effect from having any detrimental damage to the intake hose or anything like we're seeing. That's a plastic hose that I have hooked up to it, and it melted on me several times in this test. I wasn't quite prepared for that, but at this point I feel like I'm babbling, and we're looking at the same flame for too long here. So I'm going to show a couple of extra clips, and then I think we pretty much get the gist of it, of how this thing works. We're basically using a propane assist ignition, and what that does is it heats up the combustion chamber so that it helps volatilize the incoming oil, and it helps the air preheater get set up the way we want it and all that. And this little bit of time that I ran it in this test, I didn't have enough time to adjust the settings and dial everything in perfect. As I said, most of that smoke that you see is actually a fine white ash that this stuff produces when it's burned at high temperatures, and I'll try and put a clip in there of what this ash looks like. Alright, we're going to shut it down now. Okay, the pump is off. Okay, let's examine what happened here. Hushka, ishka. That was intense. I think we melted the hose going to the secondary blower, but nonetheless, you can see we was getting some very high temperatures there. All the buildup is burnt away, which is a good sign. This definitely helps out at low input flow rates. That little sucker's still going in there. I'm glad to see that design working so well, that we're holding a flame holder on the intake with waste oil. That's pretty freaking good, man. We're just gonna let that burn everything out because I want to inspect the ash buildup. We'll likely be chopping this machine apart to do a thorough examination. That's why it's made out of steel. I don't want to waste a bunch of money on stainless, knowing that I'm going to chop it up to do a inspection on the interior elements. Because like I said, there's quite a bit going on right here. Maybe we can get away with it without tearing it up. We might do another test run on this thing. Is it still going? All right, she's out. And finally, we have achieved a successful test run for inspection. One of the things we want to be paying attention to is buildup and accumulation things like that. We want to find out where the buildup lives. It's pumping some ash now, so I'm going to shut it off. I do not want to disturb the ash growth or the ash ecosystem, for lack of a better term. We want to be able to examine a natural crystallization of any crystals that may form, which does happen with these waste oil burners. I've seen some pretty strange crystal growth inside of these things. Straight columns of crystal that grow with the direction of the flow. Maybe I'll try and find a picture of that for you guys and show you what I'm talking about. Pretty sure we melted this poor thing to death. Oh yeah. I don't know how much we were actually doing with that towards the end. It's stuck inside the frickin' tube. But we did see that it is worth adding that feature, because at lower flow rates we were definitely getting a tighter, more oxidized flame, which is going to be very important where this thing's going to be running. But we're calling it a day on that test. Here is an image of the crystal growth that I mentioned. Now this thing ran for 24 hours. It was still working, but there was indeed some crystal growth. And this was running with not enough air. This was a test that was done a couple years ago to see how low we could run the thing. What was the minimum setting? We're always running things at the highest. And in this test, we ran at the minimal operating rate. And these strange crystals grew on the discharge. So all we did was remove this ring right here, and that pretty much mitigated that issue. Here is the diagram that I have thus far. I'm still on the fence of what I want to do about the atomization zone. And as you can see here, this outer tank is enshrouding the combustion chamber. And these right here are flaps that let the air in. This drawing is not complete. This is about the size blower we would need. And I just have a half-wit drawing of a man. This is like a 5'10" tall person right here, I think it was. So just to give you an idea, right here is our control box, and all the controls would be facing the man right here. This is our propane tank for our propane assist ignition. It is inverted to allow us to use liquid propane because the flow rates we need would not be capable of being furnished by a tank this small if we were to use the gas. So by inverting the tank and hooking it up, you can see here we have a propane injector. That would be a little bit longer right here. This right here is the ignition. As I said, this drawing's not finished. There's a lot to it. I'm on the fence about what I want to do about the vaporizer zone. I'm thinking about bringing this back out like the original design and getting rid of the spray plate. I don't know if you've ever seen how water from a faucet in your sink hits a spoon and it spreads it out into a fine web. I thought about doing that right here on a larger version because we have so much available infrared energy going on inside of this thing with the big fireball. But I may remove this because this is not what's inside of the unit that we currently have. Currently, this oil spout is about right here. Let me back this up some. I need to turn my snaps off. The oil spout's about right here, and the oil just kind of drips out of there, and the preheat air is coming here where you see the mouse cursor and then flies out this direction. And that preheat air is heating this tube up, and this tube itself is acting as the vaporizer. But it's prone to buildup, so we would want to design this thing, if we did that, where the back plate of this can be easily removed and someone could get in there with a cleaning tool like a brush and scrape all the crap that builds up on the outside of this after every use. Because it will probably need cleaned after every use, maybe not. If we run it hot enough, we see in here how this top zone was white with white ash. That ash will erode away from particle impact from the swirling gases, and it's self-cleaning at very high temperatures. That's why I rated it at the 50 liters per hour that we saw with a flame about this big. Because if you got a flame that's this big coming off the top, the interior temperatures are colder and they're not hot enough to burn away the ash. So this whole thing is on a skid with some 5-inch tube steel. so that it can be picked up with the forklift. And we'll also have some anchors on here that are set so it can be picked up with the crane, or however they want to load this thing onto a boat. In some instances, probably a crane is going to be setting it on a boat, but maybe not. But I wanted it to be movable with a forklift and a crane, so this is sitting on a skid. And as far as mounting it down to the boat, we could use magnetic mounts. There's a couple of different options that I was going to discuss with you. Turnbuckles or whatever might melt, so we would definitely want to use chain turnbuckles if we did use that to mount it down. I thought about putting this whole thing on a swivel so that we could aim it, either horizontal or vertical. Maybe the winds are just too high one of the days we want to run it, and we'd rather run it, at a horizontal with a fire shield. We could also put a fire shield on the top of this that's, say, just a piece of metal that's this big, and that would keep the wind directly off the flame. So this is about the size we'd be looking at. But anyway, what we are seeing here is the proper proportions, giving us that 37 cubic foot. And as I said, the way I calculated that was, so essentially, yeah, we were looking at a target of 4,260 liters per hour. And we divided that by 50 liters per hour. It came up to 85.2. So if we take 85.2 times 0.3 cubic foot, we come up with 36.63 cubic foot. And this specific design is 37.1. And it just came out to that because I wanted the aspect ratio to match the actual design. So the height versus diameter ratio is exactly as we've seen in the small prototype. And that's kind of what we got. Right here is a flame eye that would instantly shut the fuel off. If this thing were to go out on us for some reason, maybe we get some really wet material in there and we don't want to just keep dumping fuel in there. We have a drain port and a clean out port. And I'm thinking about maybe making a bigger port for a clean out hatch on the side of this thing. I don't know yet. But as long as we run it really hot, we won't need to clean it out. So this is the diagram that I've started on, and I was going to put this inside of a typical diagram blueprint with some information on it, and I do need to label everything and get it ready for a patent and all that. But before I finalize the diagram, I wanted to talk to you about the specifics. When it comes to the amount of air, we may need like 3 of those blowers that I showed you. And that was, what do we got here? Right here. Well, that's not it. This bad boy right here. We may need 3 of these to pull off the amount we want to burn. This is a 7,000 cubic foot per minute blower. But based on the calculations that I did, we would want, possibly 28,000 cubic foot. We don't need all of the combustion air from the blower because there's going to be an external flame. Some of our flame is going to come from the ambient air. So we may get away with just 2 of these. I don't know yet. I think we should consider trying it with 1 or 2 and seeing what happens, because the blower that was on the test device was 500 cubic foot per minute, and we were not running it at full power. We were running it at half power, which would put us at far less. If it was, that's only 14,000 cubic foot. That would mean we'd only need 2 of these blowers to get that. And we may want to change up the secondary air input. We may want to be able to throttle that. So we might want to have the secondary air have a blower of its own. So that's kind of where I'm at, Sam. Just thought I'd show you what I got. I didn't want you to think I forgot about you. I got really busy there for a while, but it sounds like you're in the same boat. I just wanted to let you know I didn't leave you hanging. And I am going to leave that equipment in place so that we can do a test when you get here if you want to try a vertical test with the flame shooting up in the air.